let's go back to where I think we left off. Let's see. Talk about that. Synthesis. We left off here. Um, so we left off here, and I think the last thing we talked about was a photochemical variant of Diels-Alder, and that's not possible um, under thermal conditions. You can do it, but under photochemical conditions, because of the Woodward-Hoffman rules, you can't do a 4+2 uh, photochemically. It's disallowed because you won't have the proper orbital overlap. Now, there have been some photochemical um, reactions done on 6 electron systems. There's a paper from like 1970 something, early 70s, where they did work on a system that mimicked a 4+2, but they didn't get a cyclo addition. They got like a bunch of weird products because with it being photochemical, it's going to go through a radical mechanism, and so they got a bunch of different products. And I think that paper is in on Blackboard. I posted it along with the copy of this PowerPoint. If I'm not mistaken, I posted it to Blackboard. um, but there's a way to do it, and the way to do it is to do what Hoy and coworkers have done. And this was actually posted in Nature. He has about 7 or 8 papers on this topic, but this one was posted in Nature in 2012. Uh, and he calls it the hexadehydro Diels-Alder reaction, because you don't have the protons that you see in a um, typical or traditional 4+2 cycle addition. So one of the things about this reaction is that you get these benzene derivatives, and that's this right here, highlighted in blue. A benzene is a benzene ring that has a triple bond in it, and I know that's counterintuitive, uh, because normally the geometry on a triple bond is linear, and those groups on the end are not supposed to be bent like that. But this is a verifiable intermediate. It's short lived, but it's actually a verifiable intermediate. Uh, so you get this benzene derivative, and then it aromatizes if you trap it like with a nucleophile and an electrophile, because one end of that is polarized. So one end is going to be negative. So you can trap it, attack it with a nucleophile, and then trap the anion with a electrophile. And then on the bottom, that's just kind of a variant of that reaction, where you can cyclize that 6-member ring. And if you notice, like this is kind of like your diene, and this is your dienophile. Uh, but this is will be considered a diene and not a diene. So this is a diene, and this is your dienophile or dienophile. But you can also they kind of modify the reaction by trapping it with cyclooctane, right? So when you get to the benzene, you actually can you can actually eliminate from cyclooctane to get an alkene, and put protons on both sides of that. So that's what they call a trap. So if you see the paper, it'll have a like a reaction scheme, and then somewhere in the reaction scheme it'll have the word trap, and so that's what the trap is. It's in this case a cyclooctane appears like some nucleophile electrophile pair. All right, and this really opened up like a lot of new avenues into studying arine reactivity. Right, that's what this is. And instead of an arene having all double bonds, the fact that it has a triple bond present is we call it a arine. Um, and so this is the reaction under thermal conditions, right? You take this polyion under thermal conditions, and this is the cyclic product. No, let me take that back. That's going the opposite direction. This is the cyclic product you get from that, right? Where you have this benzene intermediate. And notice the conditions. You can do it under thermal conditions, 90 degrees Celsius, uh, in deuterated chloroform for 24 hours. you get 91% yield, right? And then here, if you do it under photochemical conditions with either 254 and 300 nanometer light, and do it in deuterated chloroform, right? And your electron withdrawing group here is just an ester, methyl ester. This is the product, right? Under both conditions, you get 90%, up to 90% yield, right? Which is phenomenal. The anion is then, you can see here now, the trap is here, right? So this methoxy group is going to attack here, and then the pair of electrons will end up here. That's where your negative charge is coming from, all right? And then if you treat that with uh, methanol or CDCl3, right? You can put either deuterium here or hydrogen. That's what this is right here, and then you'll form a salt over on this side, right? And just treating this with a proton source here, you can eliminate off the methyl group and end up with the furan ring here. All right, but this is again, uh, it's not new chemistry. It's been done before, but the mechanism, this group, the Hoy group, has done a phenomenal job of tracking the mechanism and figuring out like what's happening in these particular reactions. So some of this is like a proposed intermediate, and this was published in, again, the same Nature 2012. The proposed intermediate using a manganese catalyst is, this is the product, but here is the intermediate right here, right? So this is that benzene, right? This can't stay this way, and so that's why you get this carbon-carbon bond right here becoming a triple bond, right? Because you can't have uh, this structure. It's not gonna persist, right? So this is kind of in equilibrium with this, but this is what persists, not this, right? And so from here, the cyclization part is actually, just trapping it. Like, so here you can see the trap is here, right? Oxygen attacks here, cyclizes and gives you that 5-member ring. And then you have a pair of electrons here where the TBS group ends up, right? So that's the intermediate. Um, in 1997, right, the mechanism was also probed by Bradley and co-workers. And you can see right here, it's the same type of polyion, but this is kind of like your diion, and this is your diionophile, done at 600 degrees and 0.01 torr. Now we go back here, you can see that this is done at room temperature, right? So that is a great, great innovation to be able to do it at room temperature, as opposed to doing it at 600 degrees. And then also Bergman also kind of probed or studied the mechanism, and the Bergman group, they proposed a stepwise mechanism with a diradical species rather than an arine. And so all in all, the mechanism notwithstanding, you still are able to take a diion or a triion in this case and cyclize it, right? So the cyclization happens under photochemical conditions, which is unprecedented for a Diels-Alder type reaction. All right. So you can't, because under normal circumstances, you cannot do a 4+2 under photochemical conditions. So this is a kind of an analog of a 4+2 where you get the same type of product, but you start with a different type of start material. All right. And so this is another probe of the mechanism. And you can see here it says only A is observed after the reaction, right? So it has to come from this pathway right here, where you go from here, and this is your transition state. This is the benzene that's formed, and then you form A. You don't see B, right? Which will come from this stepwise pathway where you have a diradical here, uh, and then you just quench that to get to your product. All right. All right. So another concept to think about with this Diels-Alder reaction is uh, doing it using organocatalysis. We saw an example that was organopromoted previously with silicon, um, but here This is a organocatalyzed Diels-Alder reaction. This is done by Dave McMillan. And you can see over here, this is the mechanism. It goes through an iminium ion. I don't know if you remember when we talked about organocatalysis, and that's one of the major pathways of organocatalysis is the formation of an iminium ion. So if you start with the diene, this is your iminium catalyst or imine catalyst, um, and you react that with your dienophile, right? That's going to give you the iminium species here, right? So that amine reacting with your dienophile gives you the iminium species, which then reacts with your diene and gives you this uh, norbornene type fuse ring system, bicyclic system, right? And so the catalyst itself, I mean, you can remove the iminium also, right? And then you end up with this as your product with the aldehyde in the endo position, right? So these are the catalysts that were used. All of them with Macmillan, a lot of his work is centered around taking like amino acids and amino acid derivatives and using them as organocatalysts. So these were the catalysts that were used, and then over here are the results, right? You have this alpha beta unsaturated aldehyde, cinnamaldehyde in this case, with a with this diene 10% catalyst. Again, it's not catalytic unless it's substoichiometric. So 10% is, that's a substoichiometric amount. This is done in methanol and water at room temperature, 23 degrees Celsius. And you get the endo exo product. And in this case, it looks like the exo product predominates, which is interesting because normally the endo product will predominate simply because of what we talked about earlier, those secondary orbital interactions. When you start with a cyclic diene and you make a bicyclic system, if it has a electron withdrawing group like a carbonyl conjugated to it, then it's normally going to prefer to be endo because of those secondary orbital interactions, but you don't see that here. Um, and it could very well be due to the steric bulk of your catalyst, right? Because again, you're making the iminium ion. So if you got a bulky iminium ion here, right, when you are going through the transition state, because the iminium ion reacts first with your aldehyde, the amine reacts with your aldehyde to give you the iminium. When you're going through the transition state, right, the exo may be more sterically favorable than the endo. So the steric encumbrance may override any electronic benefits you get from those secondary orbital interactions, and so that's probably why you see the exo being favored. Yeah, that's why you see the exo being favored in this case. You can see the enantiomer selectivity is too not that great, except for here you got a 93% EE with catalyst 7, which is this catalyst right here. And down here, you can vary the R group on your aldehyde, right? And the reason why this is important is because these alpha beta unsaturated aldehydes are notoriously like slow as far as reactivity is concerned. So you have methyl, propyl, isopropyl, phenyl, furyl, all of those different aldehydes give you good yields. And then you also, with 5 more percent of 7, you get really high enantiomer selectivities too, especially for the endo. So you got 90 to 93% enantiomer selectivity for the endo, exo 86, 84 up to 93%. But the ratio here remains 1 to 1, and then for the exo is 1.3 to 1 when the R group is phenyl. But it's still the same catalyst 7. Right. So here's another example, and a example to just kind of show the functional group tolerance and the utility of uh, the Diels-Alder reaction. This is your diene, so it's a hetero Diels-Alder in this case, in the sense that you make a hetero cyclic ring on this side, starting with an enol, and for this is these are your products here, right? Your R group here can range from a fluorinated aromatic ring to a uh, aromatic ring containing a methoxy, right? And then these are your other products here where you have a tert-butyl or phenyl or a like a cinnamyl type functional group here. And you can vary your aromatic on this side as well. You can see that down here, right? And so with that, with this particular reaction, you see the endo exo. Now you see it favor the endo, right? 98 to 2, 98 to 2, 98 to 2, 97 to 3, and then 98 to 2. Good yields from 61 up to 75%. And then in antidote selectivity is also very good, right? 92, 80, 84, 91, and 92. So this is catalyzed by nickel. It's a nickel catalyzed asymmetric Diels-Alder reaction, right? And the catalyst is nickel, um, this nickel perchlorate catalyst right here, and then the ligand is this DB Fox ligand right here. You can see it has like a isoxazoline or isoxazoline substituents here, and it's got this central diaromatic tricyclic system here. So that again, when you think about the ligand has to be able to chelate to your metal, and it has to be able to create kind of this cavity around the metal that causes a bias such that when your in this case your diene and dienophile are coming together, right? There's a bias in the transition state such that one of those pathways is less desirable than the other. That's what leads to your increased enantiomer selectivity, right? And this was published by Esquivius in 2007 in JACS, right? And you can think about this particular reaction. This is a really fast way to build up architecture. If you look at all the different types of substituents that are here and that are tolerated, this is a really fast way to build up like architecture that includes multiple uh, chiral centers, right? And this is another example of the organocatalyzed. I think the slides got jumbled up. This should have been with the Macmillan information. I'll fix it and then re-upload it. But this is your the proposed transition state, and this is just the scope of the reaction, right? So you have a bunch of different types of dienes that you can use, and this is an interesting entry right here because you have two dienes that are available, but the preferred diene is the diene here in this 5-member ring when you're reacting it with the alpha beta unsaturated aldehyde. So yeah, that's it. So with that being said, that's the end of. Let me move this up now, and then I'll re-upload this. I'll print it and make it into a PDF and upload it again. So with that being said, we're gonna stop here, and I want to open up the floor because in lieu of doing like a final exam,